All right, welcome to today's lesson on matrices, which, from my experience, are not everyone's favourite topic, but we'll get through them. So, I don't know if you've experienced a matrix before, but they generally look like something like this. They have rows and columns. They can be any size. They can go from a single row with some numbers. They can go to a multiple columns with some numbers. All right, they can be square like I've got here, or they can have 3 of each. Haven't drawn that very well. All right, and then just to make it pretty straightforward, they're always named for their size given rows by columns. So for instance, this one here would be 1, 2, 3 rows by 1, 2, 3 columns. So it's a 3 by 3 matrix. This one here would be a one row by 3 columns. So it's a 1 by 3. This one here would be a 1, 2, 3, 4 rows by 1 column. So it's a 4 by 1. And this one up here would be a 2 rows by 2 columns. So it's a 2 by 2. All right. So that's how we name them based off their size or dimension. And if you're ever asked about to record the size or dimension of a matrix, this is what you write down. It's rows by columns. So first thing in your notes needs to be, this is how we refer to size. All right. Now the next thing about them is that they can have what's called elements inside them. All right. And those elements are named and located according to basically a mapping reference. So this one here would be A, being the first letter, and it's in row 1, column 1. This one here would be A, and it can be in row 1, column 2. And this one here can also be an A in row 1, column 3. So you get the idea. You name each element according to its location on the grid. So this one here could be A in row 2, column 2. This one then in the bottom right corner would be A in row 3, column 3, and so on and so forth. So we name elements according to their location in the grid. And you'll be quite familiar with this because it's basic mapping notation when you're outside in the real world. All right, so you have your overlaid grid and you just name them according to that. So then if we look, or if we consider two matrices, you might have matrix A is 1, 2, 3, 4, and matrix B is 4, 3, 2, 1. All right, now even though they have the same numbers in them, they are not the same matrix because matrices are an ordered way of recording numbers. All right, and if things are not in the same order, they are not the same. Okay, so remember this for your notes. A and B down here are only the same if the elements are in the same positions in both matrices. All right. So you have to consider A and B, and you have to ask yourself, is element 1, 1 the same? Yes or no? Element 1, 2 the same? Element 2, 1 and 2, 2, are they the same? If they are not, A and B are not the same. All right. Now A and B can be the same if two conditions are met. Their rows and columns match, and elements are the same in each position. Okay, so two conditions. And only if these two conditions are met will the matrices be the same. And now we're going to have a look at some operations with matrices. So the first operation we'll look at is addition and subtraction. All right, and addition and subtraction is very easy. It's quite simply, you take two matrices and you add the elements that are in the same position. So this one adds with this one. And you record them in the same position as they started from. So 1 plus 7 sits there. And then you might have 0 plus 9 sits there. And then you might have 2 plus 10 sits there because they're in the same position as they began. And the last one is 3 plus 3. So your new matrix looks like this. You'll have 8, 9, 12, and 6. And those come from the original positions in the original matrices. All right, so top left finishes top left. Top right finishes top right. So on and so forth. And it's the same for subtraction. So we'll do the same two matrices for subtraction. All right, 7, 9, 10, 3. And again, you will have 1 take 7. Now this is, order is hugely important here. So I've done this matrix, take away this matrix. So this one has to go first. 1 take 7. And then we're going to go 0 take 9. And then we're going to go 2 take 10. And then we're going to go 3 take 3. And that will give us the final matrix of minus 6, minus 9, minus 8, and 0. All right, so addition and subtraction have to occur. To elements in same position. That's pretty straightforward to remember. All right, the only thing you need to remember or think carefully about when doing this is the fact that sometimes you'll come across matrices which are different sizes. So you might go, you might have a 3, 1, and you're trying to subtract something that looks like this. So this one's got, this is a 2 by 1, and this is a 2 by 3. And so you'd have to think to yourself, well, I'm going to be able to go top left is 3 take 7, so my matrix is going to be 3 take 7, but then how do I subtract those numbers from anything? There's nothing in the original matrix to do it. And this is where addition and subtraction are unable to be done. So a problem like this is unable to be finished. All right, so if you've come across anything like that, you would say it's not possible. Just like some operations are undefined, this operation is not possible. And sometimes the questions and the exam will throw questions like this at you, and they'll expect you to say this is not possible. All right, so keep that in mind. If matrices are not the same size, addition and subtraction are not possible. Now, sometimes you'll come across matrix calculation that involves scaling it up by a certain factor. So just like you might double something or triple something or halve something, you might scale it up by a certain factor, and that factor will sit outside the matrix and be shown like this. You might have a matrix that looks like that. This is a 2 by 2, and the scalar will sit out the front like that. Just imagine that it's brackets there, and you're seeing a coefficient out the front of it. So the way it works is this scalar just multiplies to each term inside the matrix. So it yields this new matrix that looks like this: 3 by 4, 0 by 4, minus 8. Oh, oops, I'm multiplying by the wrong scalar. Should be 0 by 3, minus 8 by 3, and 7 by 3. All right, and then that will just simplify as far as you can. So 12, 0, minus 24, and 21. All right, so this is called scalar multiplication, and it's useful if you're making a matrix bigger by a constant certain factor, and it happens to each term inside the matrix one at a time and doesn't change their position. Now, before I get on to multiplication, which is where the real heavy lifting comes into play. I'll touch on defining, and there's a video that I'll show you to do with the Casio Classpad, which allows you to define your matrices in there and makes your job a lot easier. But the book will do it as well, and it will lay out information in a question, and it'll phrase it like this. It'll say A equals this matrix. That's a 1. And B equals this matrix. All right, so it's sort of defined these matrices as a variable. So then when it comes to do questions, it'll reuse those variables multiple times throughout the question, but it won't have to rewrite the matrix because that's kind of finicky and annoying. So it will say, solve this. And you would have to go, all right, well, 2 times A means 2 times this matrix here, which will give us a matrix that has everything multiplied by 2, which is 6, 4, minus 2, and 2. All right, so it's able to put a rather complicated question into very simple terms by using a substitution for what it's been defined as. All right, so another type of question is where it uses these two matrices and it says it wants you to find the matrix X. So we can work out using inverse operations first how to find X. So we know we're going to have to multiply by 2. We don't know what X is because it's not one of the two matrices we've been given, but we do know what B is. So let's rearrange this linear equation to get X by itself. We see that X equals B take away 2A. So let's do this. Let's go B subtract 2 times A. We've already worked out what 2A is, so let's just go B take away 2A. So we have 6, 4, minus 2, 2. So I've got B take away 2A because this matrix is equal to 2 times A. So remember, elements in the same position subtract from each other. So I've got 0 minus 6, I've got minus 4 minus 4, I've got minus 2 minus minus 2, and I've got 8 minus 2. So finishing off, simplifying, I've got minus 6 in the top left, minus 8 in the top right, I've got 0 in the bottom left, and I've got 6 in the bottom right. So this is what X equals. You have found a matrix equal to X. If we were to go back to this original problem, 2A plus X equals B, we would find out that if I was to add this matrix to the 2A matrix, the answer would be B.